Set of videos, we're going to be looking at what we call systems of linear inequalities as opposed to systems of linear equations, which we have been discussing in the past here. So I'm going to mention a few things here. I say recall that for a system of equations, we are interested in solutions that satisfy all equations in the system simultaneously if they exist. So essentially, when we talk about systems of equations, we're talking about things that have equal signs in their statements. And I suppose if I were to sketch like maybe a graph here, and I say some other graph here, like a parabola, this would be two equations. And recall that when you look at the graphs of an equation, what you're really looking at are all the solutions to that equation. That is, if I were to just say pick a point off of here, x, y, right? And plug it back into its parent equation, some y2 maybe. I plug that in, I get a true statement. Okay, so what we're looking for is, are there any points that would satisfy both equations at the same time? We say in this system, you'd have one here and you'd have one here, but we say graphically speaking, solutions to systems occur where graphs of things intersect. So now, when we look at systems of linear inequalities, we're going to be looking at things that have statements like this here. We say like 3x minus 2y is less than 6, not equal to 6, or 2x squared plus 3y squared is greater than or equal to 6, which essentially, would be, this would be an ellipse here. We could go take a look at it. But we say these are both examples of inequalities in two variables, and we represent a solution as an ordered pair. Okay, so we say some ordered pair is a solution of the inequality in x and y if the inequality is true when a and b are substituted back in for x and y respectively. So basically, recall from algebra, that when we graph inequalities, it's the same kind of process that we use when we graph, equations. We're going to be graphing these, parabolas and lines the same way, but afterwards what we want to do is we want to test for solution pairs, because what I can say about this is this. We say the graph of an inequality is the collection of all solutions in the inequality, and we say in order to do this, you begin by sketching the graph of the corresponding equation, so what we've done here, and then it says the graph of the equation will normally separate or partition the plane into two or more regions. So basically, we say all the solutions have to lie on one side or the other of the graph, okay, if you are talking about an inequality. So what we need to do is we need to test a point into each one, and the reason why is because let's say I have this y1 here, and I say let's plug 0, 0 into the equation. 0, 0 is clearly not a member of the graph here of that line, so we could say plug that back into the mother inequality, and if you get a true statement, then this is true also, as well as all the points on this line, so like we'd have to shade this. But what I'm saying is all of the solutions have to lie on one side or the other, and if this was true, if this was like a valid point, then what I would say is I would shade all points on this side. Okay, so all points. And like likewise with the parabola, we say if I had a parabola, I could shade on the inside or the outside of the parabola. Let's say I shaded on the inside. What we're looking for with systems of inequalities are these regions where they shade together. And we're going to give this a name. We call this the feasible region. Another name for feasible is like doable. Okay, so the feasible region basically is the solution region, or the region containing all the points that would satisfy not one inequality or the other inequality, but both inequalities all together. Okay, so let's take a look at a few examples here. Example 1, it says sketch the solution region for the inequality y is greater than or equal to x squared minus 1. And I say start by graphing its corresponding equation y equals x squared minus 1. Thing is, this process is still the same. We'll start with this, sketch, I'm going to write it this way, sketch equation. Not even the inequality, let's sketch the equation. So y equals x squared minus 1. This is just a parabola, recognize. It's been shifted down one, it's got a k value of -1. So we say I'm going to label this. I know it opens up, so I'm going to label it underneath. We say 0, comma, -1. It's got an a value of 1. So a 1 over 1, if we put it this way, we say that like I've got a rise over a run. And it's not a slope, but it helps us get to our next point here. As I went 1 to the right, I'm going to go 1 up, basically, this says. And since I know it's a parabola, I know it's symmetrical when I get this graph here. And actually, just because I know a little bit about parabolas, I'm going to put in some more points here. Even though you could table those out and check to see it's on there. I just want a decent graph. And so we say, okay, so here's my parabola-ish thing. The right side's not so pretty. But we say, yeah, this is, I'm going to label this actually. You want to label it too. Y equals x squared minus 1. You'll notice that I use an equal sign when I labeled this graph. The thing is, this is the equation y equals x squared minus 1. When we shade on one side or the other, those are all the solutions to this guy. Okay, so when we label this part of the graph, we'll just use the equal sign to represent only these points as the boundary points. And then we say, now, what I want to do is I want to test a point, because what I know is this, all points in the region are either solutions of the inequality, or no points in the region are all solutions of the inequality. So what I'm saying is, what we've done is we've split the whole plane into two regions, inside this parabola and outside this parabola. And I want to know, okay, well, which side contains the points that make it actually accurate? Okay, so we say sketch, I'm going to write a little note here, sketch and label. I'm going to test a random point. And let's make a note here, not on the graph. And the reason why is because we know that those are kind of like, of course, give you a valid statement with the equation. Whether or not it'd be true with something like this would be whether it's or equal to or not or equal to when you look at your inequality statement. So we're going to test a point. I'm going to recommend a point, and you know what? You can't always use it, but 0, 0 because it's easy to plug in, and clearly 0, 0 is not on the graph of this right here. So we say 0, 0. Let's go plug it into the inequality. So what we say is our inequality is y is greater than or equal to x squared minus 1. Where we are now substituting for x and y respectively. We say 0 and 0. You notice it's very easy to plug this in. We get this here. We say 0 is greater than or equal to -1, which is totally true. So when we say that's the case, then I'm going to shade towards 0, 0 because 0, 0 makes it true. And actually, I'm just going to pull this out. And I'm going to recommend that when you shade, since we're going to be doing systems, lots of things shading together, let's just go ahead and do this. Let's put arrows towards the way you want to shade. Or, if you like colored pencils, you could say, hey, here's my solution region right here. So very quickly, I want to look at some pretty standard linear inequalities. Basically, that was a quadratic inequality, but most of the time we spend our time with linear inequalities, and they are of this form here. So you'll notice that you have, let me readjust that there. Now I can write on it. You have things, well, you see this right here. This is what we call standard form, and this is what we call slope-intercept form, of course. But when you graph things that are in standard form, often we use what we call the intercept method, which is basically find the intercepts of the graph, plot those, and then connect the dots, okay? We have y is greater than mx plus b, well, we have a slope and an intercept. So two other common ones we see are these, and we say that this would be a vertical constraint, and this would be like a horizontal. And this is totally cool. We love those, and they're very common, as a matter of fact. So let's take a look at two of those. It says sketch these graphs, give me the solution set. I want to represent those as a graph. So I say, give me all the solution things that would make this true. So x is greater than -2. So we say this is a vertical line. We're going to graph x equals -2, which is this vertical line here. You notice I'm making it dotted. Okay, so we're going to label this x equals -2. And it's dotted because it's not or equal to. So if you want to make a note, we say like a dashed line. If this or this, and it's solid line. If greater than or equal to or less than or equal to. So this is a good note to have in your back pocket, okay? So we say, all right, well, I want to shade one side or the other. Let's test 0, 0. 0 is not on my graph. We only have to plug in for x because we have no y's to plug in for. So we get this, we get 0 is greater than -2, which 0 is greater than -2. This is actually indeed the case. I want to say this, if you can see that it's intuitively obvious that all the x values that would make this true are ones that are greater than -2, and those lie on, hey, this side of the line, then what I can tell you is you don't have to test a point with vertical and horizontal constraints. Case in point, look at the next graph here. It's be a horizontal line, it'd be solid, and it'd be at a height of 3. So we say when we label this, recall that we want to label it with the equation y equals 3. Let's test a point. If you want 0, if you plug in 0, you get a true statement. Or you could just say, look, less than or equal to a height of 3 would be these down here. So we say all the solutions are on this side of this constraint here, or you could just, you could shade it in. So this last one here, you notice is in standard form. We could totally put this in a slope-intercept. I do want to do that really quickly. X minus y is less than 2. Just to warn you, actually, people forget this. We say this would be -x plus 2. When you divide everything by a negative, you actually have to flip the sign over, because if you do not, you won't only get the wrong thing, you will get infinitely many wrong things. So this right here would have a y-intercept of -2 and a slope of 1, and I'm just going to keep connecting the dots with the slope of 1 because really this is like a dashed line. So basically, there we go, something like this. We want to label this y equals x minus 2. And we can test 0, 0 here. 0, 0 is not on the graph, so we say this would be 0 is greater than 0 minus 2, which 0 is greater than -2. This is a true statement, so we would shade this side of the graph. And then, you know what, really quickly, I just want to say if I had graphed this in standard using the intercept method, I just want to show everybody that you get the same information, same solution. So if you plug in 0 for x, you get -y would equal 2, so positive y equals -2. And then also this, if you plug in 0 for y, you get x equals 2. So 2, 0 was indeed on our graph, and 0, -2 is on our graph. But this graph of the solution region. Cheers.